3.2 Mass-energy relationship. Let's begin. Missing mass. The very famous equation from Einstein, E equals mc squared, suggests that energy and mass are interconvertible. In fact, scientists have found that mass disappears to create energy, and energy may also turn into mass. 1. Mass-energy equivalence. In his special theory of relativity, Einstein suggested that mass and energy are equivalent and interconvertible. In the equation, delta E is the energy produced when the mass of delta m disappears, and c is the speed of light. As c is large, a small mass delta m may be converted to the great amount of energy. Example 3. The mass-energy relationship. In this example, a Hong Kong $1 coin is converted completely into energy, which amounts to 6.39 times 10 to the power 14 joules of energy. That is about the electricity consumption of all households in Hong Kong for the week. 2. Energy released in nuclear reactions. In fact, when there is energy change, there must be mass change. This is true for all cases, including nuclear reactions, as well as chemical reactions. But your science teachers in the past said that there is conservation of mass and also conservation of energy. Are they wrong? Conservation of energy and conservation of mass are practically correct in most cases, because the mass change is usually so little that secondary school laboratory can never measure. So it would be okay to say conservation of energy and conservation of mass unless the energy change is huge, as in the case of nuclear reaction. A. Atomic mass unit. So even a $1 coin, which is just 7.1 gram, can be converted into a huge sum of energy. In that case, gram is already too big unit to measure mass change. In nuclear reactions, mass is expressed in terms of atomic mass unit, U for short, which is just 1/12 of the mass of a carbon-12 atom. So 1 U equals 1.661 times 10 to the power negative 27 kilogram. In the following table, you can see the mass of a neutron is just a little bit larger than the proton. Now try to find the difference using a calculator. You will find the difference to be 0.001389 U, which is much larger than the mass of a single electron, 0.000549 U. Why? The loss in mass is changed to energy released in a beta decay. B. Electron volt. To express the amount of energy produced by a single nuclear reaction, a small unit of energy is necessary. A common unit of energy in atomic scale is electron volt, eV. 1 eV is the energy gained by an electron when it passes a 1 volt potential difference. In other words, 1 eV equals 1 E multiplied with 1 V equals 1.6 times 10 to the power negative 19 coulomb multiplied with 1 volt, and that is 1.6 times 10 to the power negative 19 joules. When 1 U of mass is converted to energy, it amounts to 1.49 times 10 to the power negative 10 joules of energy, and that is 931 mega electron volts. As mass and energy are equivalent, we may even write 1 U equals 931 mega electron volts. Note that 1 U is a mass, while 931 mega electron volts is an energy. That equation is strange, right? Example 4. The conversion between mass and energy. In the examination paper, you will be given the value of U, and the electron charge E, and the speed of light c, and the formula sheet even reminds you 1 U equals 931 mega electron volt. So you may interconvert mass and energy easily. C. Mass difference and energy. In nuclear fission and fusion, the products is usually more stable, and so the total mass of the products is smaller than the reactants. The loss in mass is converted to energy in the form of electromagnetic wave or kinetic energy of the products. For the typical fission of uranium-235, the total mass of the reactants is larger than that of the products on the right. The loss in mass is 0.192789 U, which is converted to energy as 2.88 times 10 to the power negative 11 joules, which is also equivalent to about 179 MeV. For convenience, the energy released in such a nuclear reaction can be expressed as 2.88 times 10 to the power negative 11 joules, or 179 MeV, or even 0.172789 U. In other words, you may express nuclear energy in atomic mass unit. You may notice that a larger loss in energy means the product is more stable. The energy released when a nucleus is formed from its nucleons is called binding energy. For details, read the supplementary information below. Example 5. Energy released in nuclear fusion. As energy is released in nuclear fusion, the total mass of the product of the reaction must be smaller than the reactants. So you have to find the total mass of the two sides first, and then find the loss in mass, and lastly convert it into energy. Example 6. Energy released in alpha decay. In an alpha decay, and even in an exothermic chemical reaction, there is also loss in mass. In this example, the loss in mass of alpha decay is converted to kinetic energy of the alpha particle and the product nuclei, which appear in form of heat. In this example, you have to find the number of nuclei in 1 gram of radon-222. You have to find the number of mole first, which is 1 over 222. And then, as 1 mole means 6.02 times 10 to the power 23 nuclei, you may then calculate the required number of nuclei. I suppose the chemistry students know it quite well. And if you don't, please feel free to ask your physics teacher. Do check point 2 below.